right, so let me just get the setup real quick. A bullet of mass m and velocity v naught is fired toward a block of thickness L naught and mass m. The block is initially at rest. On a frictionless surface, the bullet emerges from the block with a velocity of v thirds. Assume that the retarding force of the bullet that the block material exerts on the bullet is constant. In terms of L naught, what minimum thickness L should a fixed block of similar material have in order to stop the bullet? All right. I think we're assuming that the bullet is held in place, right? It says a held in place bullet or a held in place block. And it says that when the block is fixed, the bullet emerges from the block at V naught over 2. So let's start there. In that example, the momentum of the system is just the momentum of the bullet before it reaches the block. And then afterwards, the block was held in place. We've now tunneled a hole through the block, and the bullet emerges at half of its original speed. So this is V naught, this is V naught over 2. And the block stayed in place. It said it was fixed in place. So there had to have been an impulse on the bullet because the bullet experienced a change in momentum. So if we use impulse as our starting point, we could probably figure out how much the momentum of the bullet changed. I'm afraid that will take us down the wrong path. And the reason I believe it will take us down the wrong path is quite simply, impulse is about change in momentum, sure, but it's about force and time. And although this will tell us about force, I mean, we want to stop the bullet, it would tell us how long it would take to stop the bullet, not how far the bullet would have to travel to be stopped. So although you might think that would be the pathway to go, I would think after I wrote this down, how would I figure out the length the bullet would have to travel? And I don't think I could figure it out from here. On the other hand, I know that work equals the change in kinetic energy. If this is the work done by an unbalanced force, that would also have to equal that force times displacement times the cosine of the angle between them. Well, this would have length involved in it, a distance traveled. So if I have to choose between these two, which one do I think would work best? I think I'm going to choose the second one and see if I can find a solution that way. There's other ways to do this problem too. This problem can be done almost completely using kinematics if you want. Because all the stuff is there. You just have to figure out what the acceleration is from this force and do the problem kinematically. I'm going to use what we've been learning because I think that's the way I'd like to pursue it. But there's not just one way to do these problems. This seems to me to be 1/2 m v naught over 2 squared minus 1/2 m v naught squared. It's a change in kinetic energy. And that has to equal this retarding force times L naught times the cosine of 180 degrees. This is going to give me an expression for the size of the retarding force. This is just negative 1/2 m. Oh wait, no, I might be wrong there. This is 2 squared is 4, so that's 1/8 m v naught squared minus 1/2 m v naught squared. So that's 3/8. All right, that's negative. Any question there? That good? My arithmetic right? Do you want me to continue, or are you just writing? All right. So, again, I can get the force here. The cosine is going to produce a -1. So I get rid of that -1, and it tells me that the size of the retarding force is 3 mv naught squared over 8 L naught. Okay? Now, I'm trying to figure out how far or how long to make the block so that it would stop the bullet. So what I'd really like is for the same retarding force to be used over a longer distance, still cosine of 180, to have a change in momentum that would bring the final, change in kinetic energy to bring the final energy to 0 from our original amount of kinetic energy. Now, I have to have this in terms of L naught. So I'm going to make this substitution, because that's the size of the force I just found. Got rid of the cosine 180 and the negative sign. I've got an mv naught squared on this side and an mv naught squared on that side. And I can get rid of the 2 and make this a 4. And it looks like L has to be 4/3 the distance of the original block. So we have this set up, and we have numbers, but this problem really isn't interested in that, at least not this part of it. So 2 kilograms, 8 kilograms, frictionless surface, 0.1 kilogram, and initial velocity v. In the second experiment, an identical ball of clay is thrown at another identical 2 kilogram block, but this time the stop is removed so that the 8 kilogram block is free to move. Now, question D says, state whether the maximum compression of the spring will be greater than, equal to, or less than 0.4 meters. Is there any question about why it would be less? Okay, good. I think an energy conversation is the best way to go there. A momentum conversation I don't think would be enough. I think you'd want to say that the system is going to have some of the energy, taken away and be left as kinetic energy in the 8 kilogram block, and therefore the spring won't compress as much. E, state the principle or principles that can be used to calculate the velocity of the 8 kilogram block at the instant that the spring regains its original length. Write the appropriate equations and show the numerical solutions, but do not solve for the velocity. All right. So in order to answer this question, there's several principles that you're going to have to apply. And again, it says to write the appropriate equations and show numerical substitutions, but you don't have to solve. I think that'll be fine. I'll use the numbers that are here, if that's fair for you guys. But when the spring comes back to its original length, there's no energy in the spring. You guys understand that? When the ball of clay strikes the 2 kilogram block, energy is not conserved. But after that, energy is. Because any energy that is associated with the motion of the 2 kilogram block now can be transferred into elastic potential energy in the spring. So when we're talking about, well, what's going to be the velocity of the 8 kilogram block when the spring comes back to its original position, well, it's going to have to be when all the energy is back to kinetic, and both blocks have kinetic energy. So let's start this off. I'm going to leave it all in terms of this V, and say that the first thing we'd have to do is find how much energy does the 2 kilogram block and the ball of clay have after the collision. That's going to be first conservation of momentum to find the velocity of the 2 kilogram block. So we would do 0.1 V equals 2.1 V, 2. I'm going to need to have some designation there. And this is going to give us the velocity of this block. Good so far? All right. This V2 ends up being the kinetic energy for the 2 kilogram block. 1/2 times 2 times V2 squared. I would have to do a substitution in terms of V. And that's going to give me the kinetic energy of the 2 kilogram block. Good so far? Yep. Because kinetic energy is 1/2 mv squared. Okay. Is that all right? Okay. Now, the next thing that needs to be discussed. This block is moving this way and is colliding with the 8 kilogram block. The spring being in the way doesn't stop the fact that it's a collision. Because it's colliding with the 8 kilogram block, momentum has to be conserved, the new momentum. Now, that momentum is still 0.1 v. That is the original momentum of the clay block. But now, since the whole system is moving, the whole system has to have this momentum. So as the 2 kilogram block moves to the right, the momentum of the system is still going to be equal to 0.1 v. And this has to equal the 2 kilogram block. Oh, why am I putting 2? I'm sorry, the 2.1 kilogram block times v2. I need something here to indicate that this is later. So I'll put a L here for later, plus 8 times V8 later. Now, these are going to be changing all the time, right? The thing's going to kind of oscillate as it moves to the right. You guys follow what I'm saying so far? But it can't have any more than this amount of energy, because that's the amount of energy that was in the system. You see, this collision that's taking place now between this block and this block is elastic, because the spring can absorb the energy. So at the same time that this has to be true, 1/2 times 2.1 times V2 later squared plus 1/2 times 8 times V8 later squared plus 1/2 kx squared has to equal this amount of energy. Now I'm putting this in here because that's how much energy the spring would have at any one time. But in the problem, they indicated when the spring returned to its original length. So no energy's in the spring. Suddenly, these two equations are the only ones that matter. This is the amount of energy we have total. This is the momentum. You end up having two equations and two unknowns, but you don't know what v is. So you can't actually solve this for the velocities of either box unless you know what v is, which is why they don't have you solve it. And they don't have you solve it because that's going to be a bear, right? It's not going to be easy to do. It's going to be a monster, so I don't want to do it either. But that's how you answer the question. So what principles? Well, there's going to be conservation of momentum for sure. And at this point, after the collision, there's conservation of energy. And the fact that this is an elastic collision after the original clay ball hits the first box. E is a tough question. To get all the points, you had to list all of those things in that correct order. You had to have these equations listed, and you needed to pick some kind of way of differentiating the two velocities here. And you had to state something about the fact that the energy in the system had to reside entirely in kinetic energy of the two boxes and not in the spring. I believe it was worth 4 or 5 points that year. It was a bunch for what you have to do there. Go ahead.
So are all spring problems elastic? Like if it's a spring and it's colliding, it's going to be an elastic collision?
Are all spring problems? I should speak to this because I did speak to it in the other classes. If I were you, I would consider writing some of this down. It's worth studying. I am not saying it's on your test tomorrow. I'll be perfectly okay. Whether or not one box is moving or both boxes are moving, you should be able to, in any problem, calculate the velocity of the center of mass of the system. You have that in your notes, right? If you don't, I hate having to tell you to write things down that you don't write down, but this is something you should know. It's basically a perfectly inelastic collision. Tells you what the velocity of the center of mass would be. Bringing it up because it's going to come up in this problem. Now, in this problem, I'm going to say that just one of the boxes is moving, and it's moving towards a box that has a spring attached to it. We're going to make this fantasy land for physics, that there's no friction and it's a perfect spring and there's no sound made and the collision stores any energy in the spring. So the box interacts with the spring. The two boxes have some kind of motion, and then afterwards this box is moving off in this direction and this box is moving off in this direction, and we saw this collision yesterday, correct? Yes? No?
Yes.
Look, third period, it'd be nice if you just answered simple yes or no questions. It would help. It'd make me know that I'm not just talking into the wilderness. There is a moment where the spring will reach a point of maximum compression. It is not an uncommon question to ask how much is the maximum compression of the spring. It's a common question, actually, but not necessarily one that's easy to figure out. So I'd like to tell you how you find out what the maximum compression of the spring is. First, you have to understand that this is an elastic collision. And so there's a certain amount of energy in the system and it's going to be preserved. And the amount of energy in the system is the original amount of kinetic energy that we have at the very start. Also, this is the original amount of momentum at the very start. It's the only thing moving. Now, cart one, cart two. After the collision is over with, you can use conservation of momentum and conservation of kinetic energy to figure out the individual velocities of block 1 and block 2 without knowing what happened in the middle. This is just going to be momentum before equals momentum after, and kinetic energy before equals kinetic energy after. But if you want the maximum compression of the spring, you're going to have to be a little more insightful. First, you have to know when that occurs. And I don't mean the point in time. Like, what condition has to be met for the spring to be at its maximum compression? Now, that one's harder. Remember, the way this starts is this box was traveling faster than this box. So the moment it touches the spring, it starts to compress the spring. Now, as long as this box is traveling faster than this box, the spring compresses. Do you follow that argument? But this box begins to speed up almost immediately because the moment the spring is compressed, it applies a force to box 2. So box 1 begins slowing down, box 2 begins speeding up. So you understand there's got to be a moment where box 2 and box 1 have the same speed. That's when the spring is at its maximum compression, because box 1 is no longer catching up to box 2. So if you want, you have to find that speed. And that is the velocity of the center of mass. Or you can just treat it like you're doing a perfectly inelastic collision from here to here. Either way, I don't care which way you do this, but you need to figure out what that velocity is. That's step 1. Treat it like a perfectly inelastic collision and figure out what this velocity is, because both blocks have it. The next thing you have to do is figure out how much kinetic energy is in the two blocks. The velocity you get from what you just figured out, the velocity of the center of mass, gives these two blocks kinetic energy. You need to figure out how much kinetic energy there is. This is going to be less than the original amount of kinetic energy in the first block. It will be. It has to be. The energy goes somewhere. Where did it go? Elastic potential energy of the spring. So find out how much energy is missing, how much kinetic energy is gone, and set that amount of energy equal to 1/2 k x max squared. So step 1, find the velocity of the center of mass. Step 2, find the kinetic energy of both blocks when they have that velocity. Step 3, subtract that from the original amount of kinetic energy. Step 4, set that missing energy equal to 1/2 kx squared. Yep. So again, it's a similar problem. I start from rest, I release the box, let the box slide down the ramp. The momentum of the system before I release it is equal to the momentum after, so this system has no momentum before or after. In fact, the velocity of the center of mass of the system is 0. It stays in the middle. But the energy is conserved. So the amount of energy the block has at the top of that ramp has to be distributed into kinetic energy for both of these parts. This was on an AP exam like 2 years ago, maybe last year. I don't know, it was wickedly weird. They pulled the box down against a spring and released it. The box shoots up, hits this curved ramp that's suspended in midair, and then acts as a projectile and lands over there. Nothing new here. Right? Conservation of energy will tell you how fast the block is going here. Conservation of energy will tell you how fast the block is going there. You'll have to know how much energy is in the spring. So elastic potential energy when it's launched down there. Gravitational potential energy and kinetic here. Again, nothing new, but kids came back to me with their minds blown. You know how high it is, so now it's a projectile problem. Where you pick it up and go vertical, horizontal, where does it land? Yeah, and you'll do the same thing if I put this on your test tomorrow. When I say put, I mean, it could be one of the 5. What other questions would you ask? Oh, all sorts of stuff. What's the net force on the block as it enters that curved portion? You know what I'm saying? Or what is the minimum amount I have to pull the spring down for the block to stay in contact with the curved portion? Right, the roller coaster question just asked with this launcher. They're all the same questions. Let's see, how about this one from a couple of years ago? This one's from a lot of years ago. I drop box 1 onto box 2. How far does it compress the spring after the collision? Not terrible, right? Well, maybe terrible to you. How high does box 1 bounce back up after the collision? Some people say to the original height. It's not. It lost energy during the collision. It's going to bounce back up not so high. But, I mean, is there anything, if this was your question, would you know that when the box strikes this box, that that's a collision? And it's a perfectly inelastic collision because they're going to stay stacked on top of each other. And then you can figure out after the collision how fast the system's going, because that's going to be kinetic energy, and that the system is then going to compress the spring. But don't just set that equal to elastic potential energy because the height changed, so it also had gravitational potential energy too. You'll forget that part. You always do. You set those equal to each other. Find out how far is the spring compressed, or what is the spring constant, or I don't know. I mean, any number of things. You guys, I mean, although I've given you several permutations, there's lots more, right? There was one a couple years ago, and I could go over homework questions. You have the solutions, but do you want to see a homework question? Amir does. He's not even here today.
Can you go over FRQ 1 part C?
Sure. Did you look at the solution?
Yes.
Okay.
I didn't end up getting into solution.
Okay. Like you didn't get that answer, or you didn't look at it?
I did work and I stopped after.
So if you have a green club card, quietly pack your crap and go. Oh, great. Let's put that on the video. Oh, okay. But I'm going to finish. Fair enough? So not doing any other portion of the problem, this condition has to be met in order for you to successfully travel through the loop. And for that condition to be met, there are two forces acting here that we have to negotiate. Normal force and weight. Now, you guys make lots of little mistakes. I'm saying all the things you need to do. You start here because we've done this problem before and we've talked about this particular condition. But energy will tell you how fast you're going there. Energy won't give us the conditions here. This condition is predicated on the idea that the unbalanced force causes centripetal motion. So I have to make downwards positive because it's towards the center, and you always make towards the center the positive direction for any centripetal problem. So I get 3mg plus normal equals 3m v squared over r. Correct? Now, the minimum speed is the speed at which there's no normal force. We need to be greater than that. So I can do this as an inequality if you prefer, or I can do it as an equality. I don't care. I'm just going to do it as an equality because it's easier on me and you. Now this tells me right away what the conditions are for me to be in centripetal motion at the top of the loop. Cancel out the 3m's, and I find that my v min has to be equal to the root of gr, which we've seen dozens of times in this class. But I have to be going that fast here. All right, so back it up. In order to be going that fast here, where I have kinetic and gravitational potential energy, that block had to be traveling fast enough at the bottom to have enough kinetic energy at the bottom to successfully move to the top of the loop. This is a conservation of energy question. So 1/2 3m v at the bottom squared has to equal 3m g times 2r, that's the height at the top of the loop, 2 times the radius, plus 1/2 times 3m times v minimum squared. That's the condition that has to be met in order for the energy to be enough at the top of the loop. This is going to figure out v at the bottom. So we cancel out all the 3m's. We plug in square root of gr and get 1/2 v at the bottom squared equals 2mgr plus 1/2 times gr. Right, square root of gr squared is gr.
Is that supposed to be in there?
No, it's not. Now, I can combine all those and get 2 plus 1/2, which is 5/2, and then multiply by the 2 on the other side, which is 5, giving me vb squared equals 5gr. So v at the bottom has to be the root of 5gr. Back up one more step. This has to be the velocity after the collision. The collision that occurred between a box of mass 2m and a projectile of mass m. We want this velocity, v naught. So m v naught has to equal m plus 2m v at the bottom. So right away I see v naught equals 3 velocity at the bottom. So v naught has to be 3 times the root of 5gr. Although I remember almost all the specifics, it's a block on the end of a string that's pulled perfectly sideways and then is released in such a way that it comes crashing down and hits another block, knocking it off the table so that it could go on and land on the floor someplace. Is that the gist? Okay. So I assume you want me to do all of it? All right. So my recollection is that there's two parts in particular. Two parts in particular where I should start, and that is they ask you to figure out the velocity of the system based on it being pulled from a perfectly horizontal position till just before the collision. So that's part A, correct? I'll just leave this guy over here for part B. So question number 1 asks, what is the velocity of the block that's on the string, the pendulum, just before it collides with the other block? Right? Isn't that part A? So we have some parameters. This is L and this is mass M. I would argue that if it's being released from rest, that I have all gravitational potential energy here, and that I'm going to make that measurement relative to the horizontal, and I'm going to set my reference level to be the lowest point that this mass makes it to. Fair enough? When it swings down to the bottom, all of that energy will be in the form of kinetic energy, and that will be the initial velocity of the box just before the collision. So I will set mgl equal to 1/2 mv0 squared to find that the velocity of the block just before the collision is going to be equal to the square root of 2gl. Is that pretty good? Is that okay? All right. Now, a collision, yeah.
Isn't the block supposed to be 2?
Okay. I don't remember. That's why I asked you. But even so, that will not change my answer. Is the block that's swinging 2m?
Yeah.
Okay. Better? Okay. Now, a collision occurs, and we don't know very much about the collision. I know that the 2m block encounters another block that I assume is not 2m.
Yes.
Okay. Thank you. So, right, there's a collision here where the M block isn't moving, but the 2M block is. After this collision, which I am assuming is inelastic, I'm going to make the broad assumption that the that the 2m block is moving at a different speed than it was before. Just trying to separate these out, but I can't, so fine. So the m block has one velocity and the 2m block has another velocity. I don't know what these velocities are. I don't have enough information because in a collision, we have 2m v0 as the momentum before the collision, and then 2m times v2 plus m times v1, just naming them based on their mass. I don't know v1 or v2 from the collision. So I can't get the velocity of block 2m from momentum because I don't know either of these two velocities. I have an expression for v0. I could put that in there, but you see that there's not enough information for me to solve for either one of these right now. I'm going to need another method to figure out what the velocity is for one of the blocks. Luckily, they gave me another method. They said that after the collision, this block swings upwards, but not as far as it had swung from the start. So, something like this, and went from here, swung up an angle theta. It not going as far suggests it has less energy, and since that energy is all kinetic at the bottom, it suggests it's slower after the collision. You guys get all that? I'm allowed to have theta in my answer and L in my answer. So I think I'm using energy again to figure out what the velocity was right after the collision. Because I know whatever this velocity is, which I'm calling V2 for block of 2m, whatever that velocity is, it gave the block kinetic energy. And that when it swings upwards and comes to rest, it will have all gravitational potential energy, albeit less than it had before. So I'll do that over here, I guess. 1/2 2m v2 squared equals 2m g L times 1 minus cosine theta. I mean, this is h, but remember, for anything that's swinging upwards like this, I'm not allowed to have it in terms of h. I have to have it in terms of theta. So that's what I told you to replace it for. You need to remember that. You should have this somewhere in your, brain so you can use it. I'm not saying it's on tomorrow's test, but I am saying there's a lot of things that end up being on the test that I suggested you memorize. This is one of them. Excuse me. Thank you. Now I do need to solve this for V2, and if I get rid of that and get rid of the m, I'm going to get that V2 is equal to the root of GL times 1 minus cosine theta. And that is now the answer to question B. So this was A, and this is B. Now question C, and I even tell you, I believe, to use conservation of momentum here. So I tried to clue you in, but I'll be honest, I won't be on the test that way. But we're now asked to find what is the velocity of the block of mass m right after the collision. Well, that's where I get that. I get that from here. So this is going to be a mess. But let's go ahead and do it anyways because you guys asked. So 2m, I'll put v naught as the square root of 2gl equals 2m times v2, which we know is the square root of 2gl times 1 minus cosine theta plus m v1. We're solving this for v1. There's an m in every term, but there's nothing that's going to make this look pretty. v1 is going to equal square root of 2gl minus the square root of, oh wait, there's a 2 there, 2gl times 1 minus cosine theta. All right, that's got to be it. It's not pretty. Doesn't matter. All right. The next part of this really has nothing to do with this. So the next part is all a projection problem, right? I'm sorry, a projectile problem. So let's look at this part because there's at least one thing that I was disappointed when I was tutoring last night about this. I mean, I know we have a big expression for this, but for the time being, V1 okay? And this is H. The question was, how long does it take for this block to reach the ground? I am disappointed that you don't have this at the ready. 3 months ago, I said, just memorize this. This is how long it takes something dropped to reach the ground. Memorize it. If you don't, you're going to have to do work to figure it out. And I mean, I have no trouble showing you where that comes from, but there were reasons why I suggested you memorize things. One of them is to save you time. But if you want to do it this way, That's fine. You'll have to try and figure out, well, how do I solve for that? What do I use to figure out the time? And then if you can come up with the right conclusion, you'll have to flesh this out and indicate, okay, H here, 0 here, G here, solve for T. And then you got to pick out a appropriate motion equation that'll do that. Maybe delta y equals 1/2 at squared plus vy naught times t. And then you have to solve that for t after plugging in your info. H equals 1/2 gt squared plus 0. And you still get square root of 2h over g. It's worth memorizing. I mean, I did that nice and fast because I knew exactly what to say. Do you see why this might be worth memorizing like I told you to? For the same reason I said, memorize that h equals L times 1 minus cosine theta. Something else worth memorizing. Now, the last thing is you had to figure out where along the ground it hits the ground. So we're looking for the range. That's just the other side of this. Range is Vx times t, which for this problem, Vx is V1. And t you just found. There's nothing pretty about this, but range is going to be, open parentheses, 2 times the root of 2gl minus 2 times the root of 2gl 1 minus cosine theta times the square root of 2h over g. Oh, I'm over it already. There you go. That's that. Yay. Just mash it all together. I'd love to say this one drops down and produces something really nice and sweet, and no, it doesn't. It's a mess. It's just nightmare fuel. Not like horror story Freddy Krueger nightmare fuel, but definitely. Haven't done this one yet, so this is FRQ number 3. And I remember somebody only asked about one part of it, so I don't remember the earlier parts, but my recollection is that we've got a bullet that's fired at velocity v naught, and I can't remember. It's like, is it half the mass of the block, or I don't remember. Okay. That's when the block is free to move. And then there's the version of it where the block is held in place. So I've got this, where this is V naught. And what am I supposed to use for the mass of the bullet? Little m. And what's the mass of the block? Oh, way to go. Okay, and in the collision where the block is not held in place, the block must have some velocity after the collision, but the bullet emerges from the block at a velocity of 1/3 of v naught. Is that right? So we've got this, and hole on that side, and this is now v naught over 3. All right. I bet the first question is to figure out what the velocity of the block is. Is that true? So that seems like a pretty straightforward conservation of momentum question. We've been given lots of information from which to work. So I'm thinking our momentum is m v naught plus 0. That's the momentum before the collision, because the block isn't moving. After the collision, the block is going to be has some momentum based on the fact that we think it's moving, mb, mass for the block, vb, velocity of the block, plus the bullet, which is lowercase m times v naught over 3. We're supposed to solve for vb, so I will say that 2/3 m v naught equals m vb, so 2m over 3m v naught equals vb. That good so far? Is question B the one that says that the block is held in place and this time the bullet emerges at v naught over 2? And does it want to find the length of the block that could be used to stop the block instead? Oh, okay. So it doesn't ask for this loss of kinetic energy. Is that right?
The loss of kinetic energy of the bullet.
Okay, so still this situation where the block is free to move?
It's
Okay, so it's a new situation in which the emergence of the bullet is v naught over 2, but the block is fixed in place and its velocity remains 0 after it emerges. Is that what you're saying? And we're asked to find out the loss of kinetic energy? All right. I'm going to erase what I have written here because I don't need it unless you guys want me to leave it up on the board. All right, so this is an entirely different scenario. Momentum is not conserved here, so we can't use conservation of momentum. And if you're trying to keep track of when you can or when you can't, here it is. The block being held in place is an external force on the system. There's a force to hold the block in place, and therefore momentum is no longer conserved. It doesn't really matter because it didn't ask for anything regarding momentum conservation. But it did indicate that it wanted to find out the loss of kinetic energy of the bullet. The original kinetic energy of the bullet is 1/2 m v naught squared, and the new kinetic energy of the bullet is 1/2 m v naught over 2 squared. So if we're trying to find the loss of kinetic energy or the change in kinetic energy, these are subtle differences. The loss of kinetic energy, I just subtract these two. That would be the amount of kinetic energy lost during the collision. Now, if they wanted the percentage of kinetic energy lost, I would have to divide by the original amount of kinetic energy. I assume you guys know how to do percentages, but if you don't, you take how much is missing divided by how much there was. That would be the percent lost. On the other hand, if they asked for the change in kinetic energy, I'd have to reverse these two things and subtract final minus initial. Everybody follow? All right, so I assume you said it's just the amount lost, so I'm just doing this difference. And that's going to be 1/2 m v naught squared minus 1/8 m v naught squared, which is 3/8 m v naught squared. All right? So now it's question C is the one where I have to figure out how much bigger a block would I have to use to stop the bullet. Is that right?
Yeah, I feel like minimum thickness L so that it stops the bullet.
Okay.
When it's all fixed.
So I think this is a more challenging question. And if you're wondering where would you start, there's a couple places you could start. The bullet experiences an acceleration when it passes through the block. Agreed? You could find that acceleration. You know things. For example, you know that delta x is L naught. You know that the initial velocity is V naught and the final velocity is V naught over 2. You could find an acceleration. And then do a different motion equation after you get that acceleration to figure out how much further it'd have to travel through the block to get stopped. That's one way to do it. That's not the way I'm going to do it, but that is a way to do this problem. You might be tempted, because we've been talking about impulse, to use impulse to do this, but I think this would be a bad choice. The bullet does experience an impulse as it passes through the block, but impulse is about time and is not about displacement. Although I could probably find out an expression for time and maybe extrapolate that to use it to figure out what distance I would need. That seems like the wrong direction to go when I know I have something else that is related to displacement. So although you might be able to make a case for doing it this way, I think this is probably the harder way to do it. I think the way I would go about doing it is to do it based on work. Move that over there. I know that the work done on the bullet has got to be equal to the change in kinetic energy because there's only one force acting on the bullet, the retarding force from the block. That's going to be unbalanced, so that's net work, and it did indeed change the kinetic energy of the bullet. In fact, that's what we just found out, that the kinetic energy of the bullet was changed. Right? Delta K is negative 3/8 mv naught squared. It lost that much energy. So that's just final minus initial. Now that has to equal the force applied to the bullet from the block times the length that the bullet traveled through the block times the cosine of 180 degrees, because I'm pretty sure that force was in the opposite direction of the direction of motion of the bullet. Everybody see why I chose all those things? This means the force acting on the bullet was 3 mv0 squared over 8 L naught. Now, why would I want that? Well, pretty simple. If I want to stop the bullet in a distance L, then I want the work to equal minus 1/2 mv0 squared. I want to take away all the kinetic energy, not just 3/8 of it. Right? This would be a change in kinetic energy that would bring the bullet to rest. Everybody follow what's going on there? If not, now it's time to say something, not tomorrow. Again, this is the way I would do it. Now, once I know this, I'm going to substitute in the force. We just found the force out. It's going to be the same no matter how long the block is. So I get 3 mv0 squared over 8 L naught times L equals 1/2 mv0 squared. Just got rid of the cosine 180 and the negative sign. And I can get rid of the mv0 squared. And it looks like L is going to equal 4/3 L naught. Right, when I cancel the 8 and the 2 and get a 4 there and then cross multiply. That's it. Is that it?
Yes.
All right. Not terrible. You're talking about this one, right? So they remove the stopper so that when this piece of clay strikes the first mass, the entire system begins moving to the right. Do you understand that that's going to happen now? Now, bear with me. The clay hitting the first block doesn't conserve energy. That's still going to be 0.1 times V naught equals 2.1 times V, I'll call this V1 for block 1. Is that okay? This V1 becomes the velocity of block 1. It also becomes the kinetic energy of the system, because after this, energy is conserved. Even though these two blocks are going to act like they're about to have another collision, because that's what we did over here, right? This was the light car hitting the heavy car. The difference is they're stuck together. So they're going to stay stuck together and not separate. But it's just another collision, but with the spring in the middle, that energy is going to be conserved. So this represents the energy of the system. All right? Now, at some time in the future, we're going to have an energy equal to 1/2 times 2.1 V1 future squared plus 1/2 times 8 times V2 future squared plus 1/2 kx squared, which is how much energy is stored at the spring. This thing's going to do like this the whole time. It's going to be oscillating, and they're going to be pushing themselves together and pull each other apart, pushing each other together, and pulling each other apart. Follow along? That's going to be happening all the time. However, and I think this part is important, there will be a time in the middle of all that where x will be 0. That's what the problem is asking about. The moment the spring comes back to its original length. So every once in a while, there'll be no energy in the spring, and the energy will just be in the kinetic energy of the two blocks. Is that okay so far? Well, the velocity of the center of mass of this system is going to be the individual momentums plus the mass of the system, or times mass of the system, something like that, right? The velocity of center of mass comes from the sum of all the momentums equal to the mass of the system times the velocity of center of mass. All okay? Well, we know this. We can get the velocity of center of mass right away. It's V1. Right at the very beginning. Now, this is going to be 2.1 V1F plus 8 V2F. Technically, if I know V naught, I have two equations and two unknowns, where the unknowns are this and this. I should be able to solve for it with all of that. So I have to state all the properties we used. We used conservation of momentum for the first collision. We used conservation of momentum to figure out the velocity of the center of mass. We used conservation of energy because the spring can store energy. And we used conservation of momentum a second time to deal with the individual velocities of the blocks. But I don't have to solve this for V2, luckily. I can't solve it for V2 because I don't know what this is. And I would need that. That's what they expected in E. I would never ask that on a test because I think it's too elusive. More importantly, I don't think I would ask this on a test because I don't think that it would get out of you the kind of information I'd like. I might ask for the maximum compression of that spring, though. That I feel okay asking about because we talked about it pretty extensively. But I think this one is a pretty tough question. And I think it's very, like getting it right and saying all the things correctly, I think is elusive. Does that make sense? Okay. How about a problem where I drop a block on another block that's sitting on a spring? Do you see kind of the pieces of this problem falling together, the kind of things I might ask? Like, how fast is block 1 traveling just before it hits block 2? Seems like a conservation of energy question, right? Where the block has gravitational potential energy up there, but then when it falls to here, it's got all kinetic energy. You know, I kind of like that one because that gives me a way to figure out what the velocity of block 1 is just before it collides with block 2. So then I can say block 1 and block 2 stick together. How far does that compress the spring? Well, after the collision, they have kinetic energy for block 1 and block 2 together. You'd have to do the momentum conservation thing to get that velocity. But then that whole system would come down until the spring is compressed, where it would have elastic potential energy. But you'll forget that we're below the highest point in the problem now. So you'll have to add in some gravitational potential energy here, because it has some compared to this lowest position. Yeah, I could see that problem. I see no problem with this. It has all the things in it we talked about. You'll say it's a problem, but this is a great question. It's been on the test before. It's all the same things we've just done. I know you want a cookie cutter of the last, every one of the problems I gave you, but to do that, I would have had to give you about 15 more problems. This was on last year's AP exam. Not the block one. The block one I just showed you is from the 90s. These are all actual exam questions, though. Last year, though, or the year before, I can't remember which one, there was a circular something or other suspended in the ceiling. And you were told like this height, and you were told that you pulled this thing down against the spring and shot the block upwards so that it made contact with this and went around here and then became a projectile and landed somewhere over there.
That's crazy.
Is it? Pull it down, it's got elastic potential energy. When it makes it to here, it's got kinetic energy and gravitational potential energy. Could probably ask something about what the normal force is on the block due to the circular motion of the system. In fact, I'd probably ask that over here because the normal force is down. In fact, up here it has a different amount of kinetic energy and a different amount of gravitational potential energy. But that would tell you what the velocity is here. And it's just a projectile now. And if you have this height, you know that's going to take square root of 2h over g to reach the ground, because you're memorizing that, right? Now look, do you understand? I can't think of all the permutations that are possible. So you're supposed to just be able to look at all these and come up with some stuff. I gave you a bunch. Can I possibly give you all of them? No. And I'm not going to try. I think by the time you take the actual exam, you'll have seen every possible thing, and then College Board will think of something new. How about this one? Working with simple geometries here. I didn't say simple math, though, but there'll be no calculus tomorrow.
D12-7.
Okay, but I mean, the whole problem or just a part of the problem?
Just C and E.
Is C the amount of force experienced by the rocket?
C is the average force.
Okay, and E is...
max height.
Okay. I'm not going to do max height, but I'll tell you how to do it. Impulse equals change in momentum and force times time. They gave us the impulse of the engine. They said that this C engine gives 9 Newton seconds of impulse. And told us that the engine fires for 1.9 seconds, I believe. So if it's an average force over the 1.9 seconds, this should do it. Now, if you use the other number, you would have used 0.006. I said it was 6 milliseconds. It is not 6 milliseconds. That's like less than a blink. But 1.9 seems like a long time too. Have anybody ever shot toy rockets? But this is what ST Site says it is. So this will give you the average force. I don't know what that is. I mean, you can divide. You don't need me to divide. But you could also use this to figure out the change in momentum of the rocket, which you're going to need for the next part. The change in momentum of the rocket yields 0.250 times V final minus 0. This will be the change in momentum of the rocket. And you can use this to figure out what the final velocity of the rocket is. I don't know what this is either. Can somebody work this out real quick? Because we'll need this to do the next part. It's whatever 9 divided by 0.25 is, so 36 probably, right? 0.25 is a quarter, so 36 meters per second. Now, you have two options now. This force does work on the rocket, but this is the average net force on the rocket. This is not actually the force from the engine, right? Because we did impulse, and impulse is net force. If I wanted the real force from the engine, I should take this and realize that that's net force and say that the force from the rocket minus mg equals 9 divided by 1.9. And then add the mg to this. You find, though, that that's not adding very much. You're adding 2.5 to it because mass is 0.25 kilograms. But that would give you the force from the rocket if that's what you actually needed. We could, though, still use the net force and say net force times displacement has to equal the change in kinetic energy. That has to be true. We have the final velocity of the rocket. So we can figure out how far the rocket travels while the rocket engine is firing, because that's when the work was being done. So put this force here and put in 1/2 mv squared here, minus 0. And this will give you delta x. Or you could take your force here and set this equal to ma, and using your acceleration, you can make a set of motion equations based on that. This will provide the same stuff, but you'll get this acceleration here, initial velocity 0, final velocity 36, figure out where it lands. It's the same equation. You're still going to be using v squared minus v naught squared equals 2a delta x, which is the work energy function. However, the engine shuts off. That doesn't mean the rocket's suddenly descending. And this is why I'm not going to do the next part. When you find this displacement, you have to use a motion equation again to figure out the maximum height. So starting here, x minus whatever this displacement is, x naught, equals v naught, which is 36, final velocity is 0, and the acceleration is just negative 10 meters per second squared. You can use that to find out how much higher the rocket will go. Because at this point, the rocket engine shuts off and is being accelerated by gravity. It's going to continue to go up until it stops. That's the maximum height attained by the rocket. It's motion equations. I'm not saying it's... So this is FRQ number 4. And anybody who's ever watched my really crappy videos knows that when we do homework, I just make one long video that has all the homework questions in it from any class. So every class is asked a little bit about this one, so I know I'm addressing it again. And I'm really just talking to fill the air, but it's okay. Doesn't bother me too much. I just want you to know that this has been addressed. I'm not sure I'm going to address it, the exact question you're asking, but I'll do my best. So I see two different things that we have to think about. There's what occurred initially. The mass was pulled so that it was perfectly horizontal. Now this is L and this is 2m. Well, I can figure out how fast the block must be going when it's perfectly vertical by using conservation of energy. The block has a clear lowest point, which is the surface of the table. The gravitational potential energy here is based on the fact that it is a distance L above the table. And when it makes it down here, it'll have all kinetic energy. So between those, I can use that to figure out how fast it's going just before the collision. Now, that gives you a velocity of square root of 2gl. After the collision, it doesn't swing all the way back up to where it was. That suggests it has less energy than it had before. So it did lose energy. It lost energy due to the collision. The collision was inelastic. And some of the energy that it had got probably moved to sound and all that, but also some of the kinetic energy went into the other block, right? There was a force between them and work was done on one block from the other. So it doesn't go as high. And therefore, it must have less kinetic energy here than it had here. Why? Because there was a collision that took place in the middle. There was a block right here, right? It hit that block, and after that, that block now has some velocity, and that's where that energy went. Now, I'll continue if you want me to show you. This is why, well, let me say it this way. After this collision that occurred, right, the first block was, first block right here. The momentum of the system is 2m times v naught. That has to be equal to 2m times v2 plus m times v1, where this block has v2 and this block has v1 after the collision. I can't solve this for the velocity of the 2m block because I don't know the the velocity of the v1 block. That's why I have to use energy here. But energy will allow me to say, all right, so we have gravitational potential here, we have kinetic here, so 1/2 times 2m times v2 squared equals 2mgl times 1 minus cosine theta. And this is the assumption that you guys have memorized, that the height for something like a pendulum is based on the angle. I would have memorized this if I were you. Now, I can use that to figure out what the V2 is. V2 has to be the square root of 2GL 1 minus cosine theta. Okay? So put that there, put that there, and you get a wonderful 2 times the root of 2GL minus 2 times the root of 2GL 1 minus cosine theta. Isn't that pretty? Then there's a projectile problem. Do I need to continue? Would anybody like me to do the projectile problem? Oh, okay. Of course. I am disturbed by something when it comes to this, and I have been all day. I have no trouble calling you guys out for things that you refuse to do. One of the things you guys refuse to do is remember anything before last week. But the other thing is you won't do what I ask you to do. I suggested to you guys that you memorize a couple things. And it's just, you guys won't. This is just a standard projectile. The object has no initial y velocity. Flies off the table and strikes the ground over there. It descends a distance h. How long does it take for it to reach the ground? Square root of 2h over g. If it takes you longer to do that than what I just did, you're not doing what I asked. You're not doing your part. So when you ask me what can I do to get a better grade or do better, you can do what I ask you to do. Because if you don't know that, where are you going to start? You're just going to sit there thinking about it? This is an object drop. This is not the first time we've seen it. Maybe you'll remember that it's a projectile. And that's a big maybe. All day today I've been watching students. And no, it's not been a good predictor. And maybe you'll remember that you could break this up into two sides. Hopefully you'll remember that Vx is V1 and that Vy naught is 0 because it's just coming off the table. That's a big wish. And that delta y is h, and that acceleration is g, and that you need to find the time because it's the same here and here. And then maybe you'll do a motion equation to try and find the time because you remember Mr. Shelton saying something about this months and months ago. And hopefully, through all of that, you'll come up with what you should have memorized when I told you to memorize it months ago. Right? Anything dropped takes the square root of 2h over g to reach the ground. But don't do the things I say. Spend an extra 3-4 minutes here. And then ask me politely if you can stay longer to work on your test. I mean, the AP graders aren't going to give you that benefit, right? This also assumes that you know that where it lands is based on the horizontal velocity and the time in the air, which means yay, that's where it lands. Nothing special, nothing pretty, nothing like, doom, some percentage of R or something, nothing like that. It's just a mess. This is a messy problem. Pray they give you numbers in it. This has been on the exam. This has been on the exam a couple dozen different ways. And although this problem has some differences, some slight nuances that are different than before, it really is pretty close to the last one. If not, tell me and I'll show you how it is the same. I'm bringing this up because I can't give you every possible permutation. You won't do that amount of homework. Because I can always come up with something different. And even if I show you everything I can possibly think of, you understand that my AP is going to come up with something even different. All right. Another one? All right. Well, if there's a lull, then I'll take this one. How about this problem? All the kids in the AP physics class last year loved this question. Oh, they just adored it. And you think you're seeing some radical stuff now. I pull down on this box and release it. It shoots upwards, hitting this half circle that's just suspended in midair, slides around the inside of it, makes it to here, and then launches into the air as a projectile and lands over there. This was on last year's exam. And I'm looking at these faces. Is this new? Is this something you can't do? When I pull it down, it's got what kind of energy? I'm thinking elastic potential energy. It would be from here that I'd have to measure. That up here we've got gravitational and kinetic. Here we probably got a different gravitational and kinetic because it's even higher. And now it's got a velocity that's purely horizontal. If I know how high this is, I should be able to figure out how long it takes to reach the ground because you're going to memorize it one way or the other, aren't you? Probably not. I mean, I would love to do this problem and add to it, like what's the normal force experienced by the box while it's on the inside of that half circle thing? Of course I would. Maybe in two places, at point P and point Q. Anything new here, anything that has not been part of our curriculum in the last 2 weeks, you'll say, Mr. Shelton, that was just a weird question. I'll say this was on last year's exam. You guys will all look it up and all that. I'm just going to write questions so you can. But this is in there. Is it hard? It's no harder than the other ones. How about, this is an oldie. Oldie but a goodie. I drop a box on top of another box that's on the spring. Why? I don't know. I'm making up a problem. Could you figure out how fast the box is going just before it hits box 2? I'd have to give you some information, but it would have what? Gravitational potential there? If I know how high this is, I could set that as the baseline, figure out the kinetic there. That'd be how fast it's going. So then that box makes it down there. Maybe not. Makes it right there. It's moving downwards at some speed, strikes and sticks to the other block. What does that mean? Probably an inelastic collision. So now both blocks have a velocity downwards. Probably energy lost in that collision, kinetic energy. But then the system compresses the spring. How much? Well, down there's going to be elastic potential energy. Up here, there's going to be kinetic energy. But you'll forget that there's also gravitational because it's higher than it was when it compresses that spring. You'll forget to add in that amount of energy. And therefore, your answer will be wrong. But you should. You should not forget. How about this? It bounces back up, and this one doesn't stick. What's the maximum height it attains after it bounces back up? It's not terrible. We know it's not going to be as high as where it started because there was kinetic energy lost in the collision. But I'll know that when it comes back up, it'll come back up at the same speed it went down with. Right? Right there, because it's going to go down, store that energy, come back. It's going to come back at the same velocity. It has to. You might not know that, and you might do all the work necessary to figure that out. But you should know that the energy's got to be the same. And then this box just rises into the air, just not as high as before. Just throwing out ideas. This is like 94, 95. It's out there. No matter what we think of, they'll think of something else. So there's lots out there, lots of permutations. I made sure I gave you a little snippet of all of them. I mean, I haven't even talked about the really weird ones. How about our plain algebra and geometry questions? So there are weirder things out there, like this spring obeys a different rule. This box is moving towards that spring at velocity v. How far does this box compress the spring before coming to rest? Well, you'd have to figure out what potential energy looks like for this spring by calculating the work on it and to compress it. It's not rough, it's 1/4 k x to the fourth. Once you know that, this becomes the same problem as before. You just have to take the antiderivative of the force equation. But again, like I said, your homework has stuff in it, I agree. And I'm only using this because nobody asked a question. If you have a question on your homework, by all means. I'm not giving any calculus tomorrow, unless it's incidental in the multiple choice, like I have to deal with the motion equation because it is cumulative. Tomorrow's test is going to be all algebra and trig. Probably not even any quadratic formula. So if in this one I don't want the block to slide down, and I know that the net force on it has to be 0, then I'm just dealing with tensions here, right? And I can eventually get to the acceleration. In this one, if I don't want the block to slide down the ramp, and I ask what acceleration do I have to apply to the cart? Make up here, here's the mass. The mass is m. Now, if I don't want the block to slide down the ramp, what must those conditions be? You're smart people. You're going to make a mistake here because it's a ramp. I would encourage you maybe to remember that when you're supposed to decide the direction of your coordinate system, you align it with the direction of the acceleration, not the direction of convenience, because that's the way you did it last time. What direction is the box accelerating? I don't want it to accelerate down the ramp, so aligning it with the ramp would be bad. Do you think you got it? Because I would have done something like that. Those are the only two forces acting in the system. If I make this the positive x direction, then the net force in the y direction has to equal 0. That's theta, if theta is measured relative to the horizontal. So normal cosine theta has to equal mg. That means normal equals mg over cosine theta. Well, what good is that, Mr. Shelton? Well, this normal times sine of theta is what accelerates the box. So n sine theta equals ma. So mg tan theta equals ma, so a must be g tan theta. If I accelerate at that rate, then I can keep the box there. Funny, that angle has some limitations, right? It's not like I can make theta 90 degrees. The tan of theta is undefined, right? Which means I can't just put something on the front of a box and push it and it won't slide if there's no friction. It will slide. That's what that tells you. The math tells you that. It also tells you that if theta is 0, I don't have to touch it. It'll just sit there, right? Tells you that. Like this one was on, this was 2 years ago. This was just mean. There's 2 different versions of it too, which made it even meaner in my opinion. Because one of them I thought was harder than the other for sure. Somebody put a motor on the floor and some kind of wackadoo apparatus on the edge of this table, which had a pulley here. And then there was a cable. attached to the motor. And the other side of that cable attached to a box. A constant tension was created in the cable due to the motor spinning. The tension never changed. How much work was done on the box as it moved across the table? Seems easy until you realize as the box moves across the table, something does change. Do you see that something changes? The angle changes, right? So the work has to be based on the integral due to the change in the dot product. So even though the tension is the same all the time, the angle is constantly changing. That makes for an interesting question. And I say interesting, but what I'm trying to indicate is that we haven't done these. These are interesting. These have weird math and stuff in them. Because if you really want to understand the stuff that we're leaving out right now, a motor pulls with constant tension on a block as it moves across the table. You should be worried about this problem. This was on the exam 2 years ago. It will not be on your exam tomorrow because, again, you think we've seen lots of permutations, but we haven't. I've been careful to choose ones because when this asks how much work is done, you understand that you're going to have to integrate f dot dx because the angle between the force and the displacement is changing. This is a tough one. This has got weird geometry and weird math. We'll save the weird geometry and weird math for second semester. I'm